So yeah, as Neil just said, I'm going to explain how we can go from abstract systems modeling with an MBSE approach down into real vehicle contents with a concrete data model. I guess an obvious question to start with it is why am I talking about this? So I work for Vector in the UK. I'm going to skip the blah blah. You can read it later. But we are the leading provider of tools and embedded software to the automotive industry. So if you're involved in cooperative intelligent transportation systems, you're going to be talking to our embedded software at some point because nearly every vehicle in the road uses our software. What do we do? Well, yeah, the EE systems, electrical electronic systems of modern vehicles are becoming more and more complex. They are becoming cyber physical systems that perceive their surroundings and react to them. So they are able to start thinking about other road users, such as vehicles and pedestrians and cyclists. Of course, roadside infrastructure, such as traffic signals, and signs and all the other things that we start to get interested in the CITS space. And vehicles that drive themselves based on this kind of information are being developed right now and even being tested on public roads for better and for worse. And yeah, we provide the products that help engineers to deliver these advanced EE systems. And I guess a sensible point to pick up from Neil's presentation is how much data actually describes a modern vehicle EE system. So I've got some data from some of our customers. It's anonymized, so I can say this. So one of the German OEMs, they have 34 million artifacts that describe the systems in their vehicles. They have about 350 engineers driving this data on a regular basis, with 4 times more people kind of involved in the process. So around kind of 1,500, 1,400 people regularly involved in the EE system development process. Another German OEMs, they have about 30 million artifacts in their data, and yeah, kind of 250 people driving that, with about 4 times as many people involved in the process. And then another of the German OEMs, 14 million artifacts and 150 frequent users there. So with these kind of statistics, it shouldn't be a surprise that the kind of traditional engineering approaches that we may know and love just cannot cope with the volume of data or the complexity that's involved in this kind of development effort. The days of Excel, as Neil said, are way, way behind us. We need more capable processes and approaches. So I'm going to talk specifically about how we get down to a concrete level of description from the abstract level that Neil talked about. And it's worth mentioning that when we start, we can still think about the generic abstract description. So if we want to think about the use cases that describe how our system interacts with participants in that system, and participants are not just humans, so we can have actors, generic actors. What are the actors for our system, and what are the use cases, the touch points that we have in that system? And then for each given use case, we can start to get more concrete. So for example, if we're talking about CITS, we're probably going to be thinking about services between vehicles and the ITS system. So my use case might relate to a traffic signal service, where my vehicles are able to consume data from the ITS to understand what traffic signals are doing. And this kind of dependency, of course, we want to understand more. It's not just that they interact. We want to actually understand how they're interacting. What is the data? So who are the participants? Are they using a VLAN perhaps? What are the providers, the consumers? Within that interface, what methods are there in the service? Are there fire and forget methods? Do we have properties? Do we have getters and change notifications, even setters on those interfaces? And right down into the detail, what data types are going to be transferred over that interface? Are we transferring X509 certificates? Are we having challenge and response methods and all this kind of detail? Really important to constrain and define how the interactions go. This goes back to some of the breakout topics we had earlier as well about security. If you don't understand this kind of stuff, security just isn't going to happen. And of course, from a provider, because we have a model, we can just pull out the interesting data that's relevant for us. So this is still relatively abstract description, actually. There's a lot of detail here, but actually it's quite abstract. So let's get really down into the detail, because what we really have going between vehicles and infrastructure is not an interface. We have network signals. And here we can see I've actually done a little model specifically for today. So I have an ECU, which is performing the role of a vehicle, consuming a service which is being provided by a CITS server, which is offboard, accessed over a 5G telelink via a telematics gateway with Ethernet linking it all up. So I know CAN was mentioned earlier, but typically when we're into service-oriented stuff, CAN isn't relevant. We're into Ethernet, and many vehicles nowadays have Ethernet on board and are service capable. Of course, network signals is only part of the story. Inside the vehicle, we also have a load of wiring, and we can also get down to this level of detail in our description of the system. So really understanding the physical implementation as well. All this is great. Okay, we can describe lots of stuff, but why do we want to do this? Well, typically in a traditional approach, the design data ends up kind of everywhere. You no longer are able to understand dependencies. Tracking and managing interfaces, both in the product and in the business, can be sticky, let's say, so not the easiest thing to understand how everything really kind of ties together. And of course, while we're doing our development, our hazards, our attack surfaces, these can all change at any moment as engineering work is being done. And if you're just reviewing things periodically, well, you probably will find things eventually, but it might actually be your customers or attackers that are finding issues in your design. People typically try to work with testing to address these kind of things, but typically they tend to test at the end of a project. And all we do then is drive late change, which is another change, another attack surface possibly emerging or changing and driving new issues into the design. If you want to test your interfaces, you need to know them to the minutest detail. So you need to understand at the level of data types what's going over the network. If you want to do X in the loop, well, that's great, but you've got to design and develop X first. And usually, of course, if you're doing X in the loop, it's X on its own. It's not X with its interface to Y. And of course, it's these interfaces, which is where we typically find our problems. Really, what we need to do is really get into our design data and get an understanding from that of what's happening in our design, and validate our design before we get into development, into detailed development. So we can think of this as like a DevOps for data kind of approach. So we need to find meaning in the data. With a concrete data model, we can have meaning in the data. We can express expectations then by modeling the expected structure of our design, and then we can automatically execute checks against the data all the time to make sure that those expectations are being met. So we typically have this relationships between artifacts and our data, and we start from a particular point, a source, and we might say that each service shall participate in a use case, and we can model that, as you can see here. Or each service shall have at least one provider and at least one consumer, again, as you can see here modeled. We might even want to think about the attributes, the properties of individual artifacts. So each service shall have a non-zero ID. Again, we can define all these requirements for our design, then we can automatically test our design and make sure that those things are being met in our data. So the summary. Modern vehicle EE systems are being developed by hundreds of engineers in each vehicle company and described by tens of millions of design artifacts. Manual checking of the resulting data is just not a sensible thing to attempt. Automatic checking, though, means that expectations are able to be tested all the time, even before you start any development at all, before you get to the point of simulation or X in the loop type activities. Concrete data models facilitate automatic, always-on execution of checks via modeling of expectations and then automatic pattern matching. With concrete data models, we also facilitate the querying of data to gain new insights and understanding. So with a concrete data model, all service interfaces have a specific type associated with them. So I can query the model and say, give me all the artifacts with the type of a service interface. And then I can review those independently of everything else. And I don't get lost in what's an interface, what's an ECU, what's a server, what's a. I can really get to what I'm interested in. And to finish up, yeah, I'm a software vendor. So if you want to know more about everything I've just talked about, please let me know. The email address is on the slides. That's it for me.
Thank you so much, Ian. We've got time for a couple of quick questions, or maybe just one quick question. 2 minutes. Matthew.
Okay. There's one comment from Neil. One of the advantages of MBSE approach is that you're able to start test, including security and safety simulation and testing at a very early stage, typically at concept level. So I think that's adding to what you said. I would like to ask, what is the biggest headache that you foresee for future vehicles systems as they need to integrate with the infrastructure?
So it is, so part of my job description is diagnostics, which covers software update. And of course, if we need to change interfaces, there is some complexity potentially in terms of version changes in interfaces and making sure that there is both forwards and backwards compatibility, because you can go out on a Sunday and you can see 1920s Bentleys driving around on the roads, 100-year-old cars on the road, and that is going to continue. Hopefully, we don't build products to fail in 5 minutes. So the cars that are built this year that maybe have a low amount of connectivity, our infrastructure is going to have to cope with them for potentially 100 years. Or we've got to be able to update the cars to cope with the new requirements of infrastructure, assuming that the cars can do the stuff that the infrastructure wants them to do, of course. So that's the big challenge. It's the forward compatibility and backward compatibility of vehicles and infrastructure, and the constraints of hardware. So changing software is easy. Changing hardware is really, really, really hard.
Okay, thanks for that, Ian. One other thing, you mentioned data, and towards the end of your discussion there, I think that's a vital issue. What is your view on data quality?
Yeah, so this is kind of one of the reasons for we argue a concrete data model helps you, because you can describe what your data should include and then check that your design data actually does include those things. So I gave the example of relationships and attributes, but you can really go from the top down. So really go all the way through the model and try to find those things. So quality is, it's a design problem, but you should design your design, really. So what should your design include is kind of a step one. So in systems engineering, there's often this kind of phrase, which is solve the right problem, solve the problem right. So yeah, understand your problem, define what the problem is you're trying to solve, and then solve it. And that applies to your design process as well as actually your design.
Okay, thank you, Ian. Have we still got time, Stephen?
Yeah, we can take one more.
Okay then. What support do you need from roadside technology and systems from highway authorities?
So I guess the main thing to allow vehicles to interact with infrastructure is standardization. Without standardization, it will be a bit of a wild west. We saw this a little bit with vehicle charging. So back in the kind of mid-2000s, I was working at an EV company, kind of before the IEC published their charging plug standard, and those vehicles in the late 2000s, kind of everyone had their own charging plug. Eventually, the IEC actually got their act together and issued the standard, and now everybody seems to work with the IEC standard. But yeah, that's the big challenge, is going to be standardization, I think. and getting everybody to buy in, which may need then regulatory enforcement. So type approval approaches.
Okay, thank you very much, Ian.